All right, so let's jump into lesson 3. So lesson 3 has to do with interpreting functions in context. So for the most part, we're going to be talking about real world situations that are represented by functions and then having to answer some questions surrounding them. So key features here says functions can be represented in multiple ways. Key features can be represented through verbal descriptions, tables, and graphs of functions. These key features include whether the functions increase or decrease, where the intercepts are located, and the end behavior of the function. Knowing certain features about a function can also help in creating the graph that models that function. So we're going to take a look at this sample question here. It says, during the first month of a year, a company had expenses totaling $8,000. The company had additional expenses of $4,000 for each month that followed. Which graph best models the relationship for the first 6 months of the year? So our key here is that at the beginning, the first month, they started with $8,000, right, in expenses. And then when we see the next piece of information, it says $4,000 for each month. Well, if we look at all of our graphs, the months are on the x-axis. So this here, 4,000, is going to be what we associate with each month. When we see the word each, we're talking about multiplication. So if we were to kind of write function here, we're looking for 8,000, and then each month, it's going to increase by 4,000 plus or times however many months it's increased by. So if we're looking at 2 months after they initially started, we'd have 2 times 4,000 and add that to the initial cost of 8,000. So if we take a look here, we're looking for which one of these functions during the first month of the year had a total of 8,000. So that means at month 1, we're looking for the expenses to be 8,000. Well, for A, at month 1, the expenses are 4,000. Not going to be our answer here. B, the expenses for month 1 were at 8,000, so possibly. C, our expenses for month 1 were at 8,000, so possibly. D, at month 1, they had expenses at 12,000. Not going to be our answer. Now we're looking for each month, it goes up by 4,000. So if we look at choice B, from 1 month to 2 month, we went from 8 to 16,000. That's an increase of 8,000, not 4,000. So it's not going to be our choice here, which leaves us with choice C. From month 1 to month 2, it went from 8,000 to 12,000, which is an increase of 4,000. So that's our choice. So this function here, right, which is a set of points, represents a situation in that problem there. So it says graphs of linear functions have key features involving intercepts and whether the slope of the graph increase or decrease. Graphs of exponential functions have key features involving whether the function increases or decreases as well as its end behavior. The end behavior of an exponential function describes what happens to the function as the domain values approach 0 or as the domain values increase and approach infinity. So if we look here, an office manager bought a computer for $1,000. For tax purposes, the office manager depreciates the value of the computer by 75% each year. The function f of x models this situation. The graph of f of x is shown below. Which statement is true regarding f of x? So when we're looking at this here, this is an exponential function, right? We can tell because it's got a little curve to it and it continues to decrease here. So with our exponential function, when it's decreasing like that, as we go from where we started to where we end, the rate at which it decreases also slows down. If we look at this curve, it's kind of leveling out here. So which statement is true? F of x decreases the most from year 0 to year 1. So if we're looking at that decrease, it's from about here to year 1, which is about here. So from year 0 to year 1, it went from about 1,000 down to about $750, which is a decrease of $250. That's a big jump here. So possibly it could be A. B says it decreases the most from year 5 to 6. So if we're looking at year 5 and year 6, That's a decrease. If we look here, that's about $250 down to this one here is just under 200. So we could say maybe $190, which would be a difference of only 60. So it definitely didn't decrease the most between years 5 and 6. C, f of x decreased by the same amount each year. Well, we saw that it's different between years 0 and 1 and 5 and 6, so that's not our answer. And f of x decreases by a greater amount as each year as x increases. So as our x's increase, does it decrease by a greater amount? No, because between years 5 and 6, it was actually less than between years 0 and 1, which means that it decreased the most from years 0 to 1. So limitations. For some functions, the domain may be limited by specific values of x depending on the situation. For other functions, the domain will be all real numbers. Suppose a clerk earns $18 an hour. Since a clerk cannot work fewer than 0 hours and cannot earn fewer than $0, the domain and range are both real numbers greater than or equal to 0. Right? So a clerk can't work negative hours and can't earn negative dollars. So we make sure that domain and range are equal to 0, greater than or equal to 0. So now I'll take a look at the sample question here. It says an online store charges $30 for a 20-page photo book plus $2 for each additional page after 20 pages. The function f of x equals 2 parentheses x minus 20 plus 30 models this situation. Describe any limitations to the domain and range of this function. Well, if we're looking here, if we wanted to determine any limitations, we could read what they wrote here. Substitute different values of x into the function and evaluate. So when x equals 0 pages, a negative cost results. But it doesn't make sense to have a negative cost because you would never buy a book with 0 pages in it, right? So 0 is not part of the domain. So a negative cost occurs for all x values less than 20. So the domain is limited to all rational numbers greater than or equal to 20. Given this domain, the range of the function is all rational numbers greater than or equal to 20, right? If you're looking for a book and it starts with 20 pages, that's the lowest that it can be, right? So our x has to be greater than or equal to, the lowest that it could be is 20. We do have the ability to add more pages for $2 additional dollars, but we can't have less than 20 pages. So the next one here says for the function in sample 3, where x is greater than or equal to 20, what is the meaning of the solution that f of x is equal to 50? So if we're talking about f of x equal to 50, remember, we have our function here, and then 50. X here, right, is our domain. So this would be our page numbers, right? So we don't know how many pages we put in here, but then here our output or our range is the cost. So if we're taking a look here, if it was $50, it means that the cost of this book was $50. So if we take a look here, it says the cost of a 30-page book is $50. That's going to be correct, right? So we don't know necessarily what the input is, but we know that the cost is $50. So if we take a look here, the range of the function is equal to 50. Well, the range of this function can change depending on what our input was. So that's not it. Domain is equal to 50. Nope, because we know the domain is all x is greater than or equal to 20. And the cost of a 50-page book is 90. Well, that doesn't have anything to do with what we have here. So that's not going to be our answer either. So it's choice A. All right, moving on to a rate of change. So a rate of change shows the relationship between two quantities that are changing. This change can be constant or the same, or it can vary. So the rate of change for a linear function is typically constant, while the rate of change for a nonlinear function, such as an exponential function, typically varies. So the rate of change for a function is positive when its graph is sloped upwards or curves upwards, negative when it curves downwards. So what we mean, right? Positive means that as we go from left to right, it's going up or even curving up. Negative if it's going down or curving down. 0 when it's horizontal or flat. Undefined when it's a vertical line there, and gradients where its graph is the steepest. So if we had an exponential function, right, the rate of change would be greatest towards the end here as opposed to at the beginning. But with a linear function, it's constant throughout. So slope is a measure of rate of change. The formula we use for slope is y2 minus y1 over x2 minus x1, or we can say the change in y over the change in x. So we look at how does the y value change as the x values change. So now if we take a look on the next page here, we're going to take a look at the average rate of change. So the average rate of change for a function with varying rates of change is the slope of the straight line formed between two specific points on the graph. So the average rate of change can be found from a graph or table of values representing a function. So here it says, the Hillmans are taking a trip. The graph at the right shows how their distance from home has changed over time. What is the approximate average rate of speed in miles per hour during hours 2 through 6 of the trip? So from hours 2 through 6, we see that it's not a constant rate of change, right? As our slopes change from 0 to an increasing slope, then over to 0. So if we want to find the average rate of speed here, right, we're taking that straight line from B to D, and we're finding the slope of that line there. So the way that we do that is we take our point at D, which is 6 and about 300, and we're going to find the slope with our point at B, which is 2 and 150. So we have our point 2, so this is our x2, y2, our point 1, x1, y1, and we'll find the slope. So remember our slope is y2 minus y1 over x2 minus x1. So our y2 is 300 minus our y1, 150, divided by x2, which is 6 minus 4. This gives us 150 divided by 6 minus 4 is 2, which works out to be 75. And then these are miles per hour. And, oh, sorry here. We're going to make a mistake. Oh my goodness. Let's go back here, back. My apologies. If you take a look here, this isn't minus 2 here. Our x value is 2. So I was jumping ahead here. So we have 6 minus 2, which is 4. Then 150 divided by 4 gives us 35 miles per hour, which is our correct answer, which is choice A. All right, so if you're taking a look there, choice A. I guess we don't need that then. So again, you're just finding the slope of the line using the endpoints for the time that they gave you, which was 2 and 6. All right, looking below. Below it says, the table below shows the rate of change per hour to park in a garage. What is the average cost per hour to park in this parking garage? So again, if we want to find the average cost per hour, right, we could take the total cost in this table here, our x values, and divide it by the change in y value, because we did start right at 0 hours and you would start at $0 before you parked there. So we could just take $7 and divide it by 3 1/2, and 7 divided by 3.5 is going to be 2. So choice B is correct for $2. Now, if you're wondering how do we get this 7 over 3 1/2, right? At the beginning, before you park there, we have 0 and 0. So we can just go through, and this could be 7 minus 0 minus 0, but we can kind of skip that part there, divide it, and get $2. So choice B is correct. All right, so now we're going to take a look at some of the practice problems. So the first practice problem here says, Jacinta participated in an experiment. At time 0, she collected bacteria and placed it on a dish. She counted the number of bacteria on the dish each half hour for the next 3 hours. The table below shows the number of bacteria on the dish each half hour. So at 0 hours, right, we don't have the number of bacteria, but at time 0, she had collected bacteria, so there were bacteria on that dish there. So which statement involving this experiment is true? At the start of the experiment, there was 0 bacteria on the dish? No, because that is where she collected some bacteria and she counted as it increased. As time increases, the number of bacteria decreases. So if we're looking here, as time increases, it means we're going down the table. If we look at the number of bacteria goes from 14 to 20 to 28 to 40. So it's actually increasing. So it's the opposite of B here. C says, as time increases, the number of bacteria increases. Yep, that looks good. And then at the end of this experiment, there will be 160 bacteria in the dish. We don't quite know that because we don't know exactly when it's going to end. So take a look at C. As time increases, the number of bacteria also increases. And that's your correct answer. Next problem there says that Ray read that the value of a car decreases by 60% of its current value every year. Ray bought a new car for $25,000 this year. He wants to show the value of his car by graphing its values on a coordinate plane. Which would be appropriate domain for Ray to use on the graph? So if Ray was creating a graph, right, he'd have his X values and his Y values. On this side here, we'd have the value of the car, right? And it starts at 25,000 is the highest it's going to be. So we'd have all the way down to 0 here. Then if we're looking at the X value, we're talking about time, right? And we're talking about years. So what would be an appropriate domain for time in years? All real numbers. Well, we don't want to include our negative numbers here because the value of the car wasn't higher before he bought it, right? Right when he bought it, it was at its highest point. So we're not going to do all real numbers because we don't need negative numbers. All real numbers less than 25,000. Well, again, that would include our negative numbers here, so we don't want to do that. All real numbers greater than or equal to 0. So that would be from here and continuing on. That looks like a keeper. And all real numbers between 0 and 25,000. Well, I'm sure he's not keeping this car for 25,000 years. So I think we can just keep it at all real numbers greater than or equal to 0 as our domain there. And then we'll see the graph, right, which will show us something similar to this here, showing that decrease in value over time. All right, moving along to number 3. So number 3 says, in the table below, what is the average rate of change in temperature over the interval from 5 to 15 minutes? So remember, average rate of change, we're just going to take these 2 points on our table or 2 data pieces on our table and find the average rate of change. So if we have our time, this is like our X values, and our temperature is like our Y values. So here we have our X1, Y1, and then X2, Y2. So to find our average rate of change, we use the slope formula. So Y2 is 45 minus Y1, which is 60, over X2, which is 15, minus X1, which is 5. So if we continue on here, 45 minus 60 is negative 15. 15 minus 5 is just positive 10. And then 15 divided by 10 is going to equal negative 1.5. And then this is degrees per minute. So if we're looking for our answer, choice D, negative 1.5 degrees per minute. A says that Jasmine is a hairdresser who rents a station in a salon for a daily fee. So when we're looking at this daily fee, right, this is going to be a constant. So that means each day she has to pay a certain fee. The amount of money, f of x, Jasmine makes from any number of haircuts, x, so it's important to see that x is our number of haircuts a day, is described by the linear function f of x equals 45x minus 30. Which statement is true? So when we look at this here, equals 45x minus 30. The first thing is we can identify our constant. The constant is what doesn't change, right? So it's not multiplied by a variable. So the constant is how much the daily fee is. So here we could say the daily fee is equal to $30. Then remember, X is the number of haircuts, right? So if we're looking at the coefficient for the number of haircuts, that's how much she makes per cut. That's the amount of money she makes per cut. We multiply that by the number of haircuts, and that's how much money she would make after we subtract the daily fee. So if we're looking at these different ones here, we have A says a haircut costs $30 and the station rent is $45. No, because we said the station rent was $30, not our answer. B, a haircut costs $45. Yep. And the station rent is $30. This is our answer here. C, Jasmine must do 30 haircuts to pay the $45 rental fee. That doesn't have anything to do with what our function has given us. And then Jasmine deducts $30 from each $45 haircut. For the station rent, that would not be true because we're not multiplying this negative 30 times the number of haircuts. So it's just a one-time subtraction there. So again, our answer is choice B. Next one here says, which graph has a rate of change equal to 0? So rate of change equals to 0 means the slope is equal to 0. Slopes that are equal to 0 are horizontal lines. If we take a look here, the only choice with a horizontal line is A, right? As we see, our line there is flat. C has a negative slope, so it'd be a negative number. B has a positive slope, it's increasing, so it'd be a positive number. And then D, the slope is undefined because it's a vertical line. So the slope of 0, or the rate of change equals 0, is choice A. All right, so now we're going on to number 6. So number 6, which is the last question in this lesson here, says the temperature of the water in a lake depends on its depth. When the depth of the water is 2 meters, the temperature of the water is 6.4 degrees Celsius. When the depth of the water is 5 meters, the temperature of the water is 4.0 degrees Celsius. Sketch the graph that shows this relationship. So if I was making a table here, the depth is going to be our X values with the temperature being our Y values. So the first data point they gave us was at a depth of 2, the temperature of the water is 6.4. Then they said at a depth of 5 meters, the temperature of the water is 4.0. So if I was to graph these 2 points on here, we'd go 2, then up to 6, and about halfway, just under halfway to 6.4. And then our second point is 5, and then up to 4. So if we're going to sketch a graph of this relationship, right, we can connect these with a line that goes all the way over to our y-axis here. So if we're taking a look here, what does the y-intercept of the graph we sketched in part A represent? So at here, what does this point represent? At 0 meters, the temperature is 8 degrees Celsius. So at 0 meters of depth, right, you're talking about the surface or the top of the water. So I'd say like the temperature at the surface of the water and then we see here is about 8 degrees Celsius. So that's what it would represent in this problem here. All right, so this is the end of lesson 3. So come back for lesson 4, and then you'll be ready to take your quiz for this week.